Somewhere out in the universe, about 570 million light-years away, there is a galaxy that looks almost too perfect to be real. It has 9 complete rings arranged around it in a near-perfect bullseye pattern, and apparently none of our standard explanations for how galaxies form can fully account for what we are seeing. This is not a computer-generated image. This is not an artistic illustration. This is a real photograph taken by the Hubble Space Telescope of a galaxy called LEDA 1313424, now also known as the Bullseye Galaxy. And the more scientists look at it, the more it seems to challenge everything we thought we understood about ring galaxies, dark matter, and the invisible forces that shape the cosmos around us. If this sounds fascinating to you, hit subscribe right now because we cover discoveries just like this every single day. To understand why this particular galaxy is so unusual, we first need to step back and look at the broader picture of ring galaxies in general. A ring galaxy is essentially what the name suggests. It contains a large, roughly circular ring of stars wrapped around a central core. These galaxies are already quite rare in the universe. Only about 1 in 10,000 galaxies actually looks like this. And even among those rare cases, most of them are still somewhat difficult to explain, because in many situations, scientists are not entirely sure how the ring formed in the first place. But what makes the Bullseye Galaxy so extraordinary is not just that it has a ring. Most ring galaxies that we find contain 1, or possibly 2 rings, and sometimes those rings have somewhat irregular or unexpected shapes. The Bullseye Galaxy, by contrast, seemingly has 9 perfectly concentric rings, all structured in a remarkably organized pattern around the galactic center. This is something astronomers have never seen before, and as of 2026, it remains genuinely unprecedented. It is apparently forcing researchers to rethink some of the most fundamental assumptions about how these kinds of structures possibly come to exist at all. To really appreciate why this is such a problem, it helps to first look at how scientists believe more typical ring galaxies form, starting with one of the most famous examples ever discovered, the Higgs object, first identified back in 1950. That galaxy has a central core of older, yellowish stars, surrounded by a vast, nearly perfect circle filled with extremely young, hot, and blue stars. Between the core and the outer ring, there is almost nothing, a sort of empty, dark gap. For a very long time, the leading explanation for how Higgs object and galaxies like it might have formed was some kind of a massive gravitational collision, something resembling what happens when you drop a stone into still water. The object hitting the surface creates outward-moving ripples as the disturbance transfers energy through the fluid. Scientists thought that something very similar might happen with galaxies when a smaller companion galaxy, sometimes called a bullet galaxy, passes directly through the center of a much larger one, creating a gravitational shock wave that moves outward and triggers the formation of new stars wherever it compresses the surrounding gas and dust. And for many ring galaxies, this explanation seems to fit reasonably well, partly because we sometimes even find the culprit companion galaxy still somewhere nearby in the vicinity. The bullet passes through, the ripple spreads outward, the gas and dust get compressed, and a burst of star formation happens along that expanding wave. That would explain why these rings are usually full of very young, very hot, very massive stars, but this collision model does not seem to apply equally well to all ring galaxies. Even going back to the Higgs object, something doesn't quite add up. The ring there is perhaps a little too perfect, and there is no obvious second galaxy anywhere nearby that could have played the role of the bullet. And so the question there remains unanswered for now, even if most ring galaxies do fit the collision picture. With that background in mind, we can now look more carefully at what makes the Bullseye Galaxy particularly confusing. It is a large galaxy, about 2.5 times the size of our own Milky Way, and as mentioned, there is apparently a potential impactor galaxy nearby, and there even seems to be a faint trail of gas connecting the two objects, which could look like a smoking gun for a past collision event. According to the initial model, a small dwarf galaxy might have passed through the center of the bullseye around 50 million years ago, and the ripples from that impact would have generated the 9 rings we observe today. Each ring, under this picture, would be a separate ripple traveling outward from the point of impact, very much like the concentric waves spreading across the surface of a pond. At first, this sounded like a reasonable explanation. But a follow-up study by researchers Pierre Siquier and Yuxing Zhao began to reveal that the math here simply does not seem to hold together. The problem centers on the outermost ring, which sits approximately 230 light-years away from the galactic center. If the collision really did happen around 56 million years ago, then that outermost ring would have had to travel outward at a speed of over 1,200 kilometers per second to have reached that distance in that amount of time. That speed is actually faster than some of the hypervelocity stars we have detected in our own Milky Way galaxy. But according to standard physics, the ripples produced by a galactic collision should move much more slowly, perhaps reaching a maximum of around 55 kilometers per second. So there is apparently a discrepancy here of roughly a factor of 20, which is extremely difficult to dismiss or explain away. And beyond just the speed issue, the shape of the rings themselves also does not match what the collision theory would predict. Under that model, as rings travel outward from the central impact point over millions of years, they should begin to blur and overlap with each other, creating something much more smeared and indistinct. But the 9 rings in LEDA 1313424 are remarkably sharp and remarkably distinct, which is not at all what the standard collision picture would lead us to expect. Because the collisional explanation leaves these significant gaps, scientists began to consider other possibilities, and the one proposed in this particular study is both interesting and genuinely exotic. What if the rings are not caused by a collision at all, but instead by a specific and unusual type of dark matter, something that scientists have been searching for a long time and can only detect through its gravitational effects on the matter around it, never by directly observing the particle itself? In this alternative explanation, dark matter is not simply a large diffuse cloud filling a galactic halo in the way that many models typically assume. Instead, it might possibly organize itself into perfectly circular tubes or filaments inside the disk of a galaxy. These shapes would apparently arise because the dark matter particles fall in and out of the galactic gravitational field, essentially falling over each other and creating regions of significantly higher density. If this is correct, then the 9 rings we see in the Bullseye galaxy are not ripples spreading out from a past collision at all. They would instead represent a visible imprint of the dark matter interacting directly with the galaxy's gas and dust, with the gravity from these otherwise invisible particles pulling that material together into the star-forming rings we can actually see through our telescopes. This would possibly explain why the rings are so sharp and perfect, and why they are apparently not moving at the impossibly high speeds that the collision model would require. But for this explanation to work, it needs a very specific kind of dark matter particle. The model is built on the concept of axions, which are extremely light hypothetical particles. Under this framework, axion dark matter would be so light that enormous numbers of these particles would combine and collectively start to behave like a single massive quantum entity, something referred to as a Bose-Einstein Condensate. This kind of collective quantum behavior can also produce ripple-like wave patterns. And unlike the rings that would be generated by a galactic collision, these quantum origin ripples would form naturally inside galactic halos as a result of the dark matter's gravity combined with the rotational motion of the galaxy itself. In this picture, the axion particles are not drifting around randomly. They seem to organize themselves into a large, slow-moving, swirling flow that generates folds and waves in the matter around them. And intriguingly, according to the authors of this study, the 9 rings we actually observe in LEDA 1313424 appear to fit this axion dark matter model quite well. The suggestion is that these rings might represent a fundamental physical property of dark matter inside certain galaxies, and that instead of forming a smooth spherical halo, the dark matter there has arranged itself into this distinctive rippled structure. If future observations confirm this axion dark matter interpretation, the consequences for science would be extremely significant. It would provide some of the strongest evidence yet gathered for the existence of very light dark matter particles, which are something that physicists and cosmologists have been theorizing about and searching for decades. Dark matter makes up an enormous portion of the total matter in the universe, and yet we still do not know what it actually is at a fundamental level. Finding a visible, observable imprint of it in the structure of a galaxy would be a genuinely major breakthrough. It could also change how we think about ring galaxies more broadly. If dark matter can organize itself into these ring-like structures inside certain galaxies, then ring galaxies as a category might not simply be random collisional accidents, but instead might represent something more fundamental about how some galaxies are physically organized at the deepest level, with dark matter actively shaping their visible structure from the inside out. This model would also offer a potentially satisfying explanation for cases like the Higgs object, where the collision picture has always seemed incomplete because there is no obvious impactor galaxy to be found. It is worth noting that this does not mean all ring galaxies would be explained by axion dark matter. We know with reasonable confidence that some ring galaxies do form as a result of actual collisions, because we can see the companion galaxy nearby and observe the trail of disturbed material connecting the two. But in those cases, where the rings are too perfect and no collision partner can be found, the dark matter explanation now seems like a more serious possibility worth investigating in depth. For anyone interested in how the universe actually works at a fundamental level, this galaxy represents one of the most genuinely compelling open questions in modern astronomy. It sits at the intersection of galaxy formation, particle physics, and our search for the nature of dark matter, which means the stakes involved in understanding it correctly are quite high. For now, the Bullseye Galaxy remains one of the most intriguing and unresolved mysteries to have emerged in astronomy over the past several years. Whether these 9 rings turn out to be the aftermath of an ancient collision or something far stranger, a visible map of quantum dark matter woven into the fabric of the galaxy itself, we will likely learn a great deal more once astronomers are able to observe this object across additional wavelengths, including infrared, X-ray, and gamma-ray observations. Either way, it is clear that we still have quite a lot to understand about how objects like this form and why some galaxies can look so remarkably different from anything else we have encountered so far.